So this video lesson is going through the force problems, practice problems. So you should have already copied the first slide, which is about solving force problems. And through this video, I'm going to be doing the 4 practice questions. So question number 1, 2, 4, and 6. The other 4 are for you guys to try on your own, and I have included an answer key as well. So we're going to start with practice question number 1. So practice question number 1 comes from that forces problems slide deck. And so practice question number 1, we have a locomotive. And so we have the train, and it's pulling a train car. And so I'm going to start by drawing a picture of what we've got going on. So I'm going to start with my locomotive. Okay. And I have some sort of cable that's then attaching it to my train car. Okay, and in the problem, I know that the locomotive has a mass, so this is my mass of my locomotive, of 6.4 times 10 to the 5 kilograms. And I also know the mass of the train car, so we're going to call that MC. So the mass of the car is 5.0 times 10 to the 5 kilograms. I also know that we're accelerating at a rate of 0.12 meters per second squared. We're traveling to the west, which means I can add my motion into my diagram. So we're traveling left because that's going to the west. And I'm also told in the question, no friction. Okay, so it says assuming negligible friction, so we're going to assume no friction. All right, once I've written down all of the information that my problem is giving me, I want to make sure that I have a free body diagram for each of my objects. So both my locomotive and my train car are resting on train tracks. So they both have a normal force. Okay, so I'm going to call the normal force on the locomotive FNL and the normal force on the train car FNC. They both have an FG. And again, I'm going to label those FGL and FGC. Okay, the locomotive has an applied force acting on it from the engine of the train. And there's a tension force that's pulling back via the cable that's attached to the train car. The train car has that same tension force. And so they're both T because they're actually the same force. Just one is pulling backwards on the locomotive and the other is pulling forwards on the train car. And so the first part of this question is asking me to calculate the net force on the entire train. So looking at the whole section, everything that's attached to each other. So we are looking for F net, and we know that our F net, we have to look at it on either the x-axis or the y-axis. Since our motion is happening on the x-axis, we're going to look for F net x. So our F net x, we're going to add up all the forces that we have on the x-axis. So we have our F applied, and that's going in the positive direction, the direction of my motion. And then I'm going to subtract my tension from my locomotive. And then I'm going to add the tension from my train car. Because tension from my locomotive is going opposite my motion, but tension from my train car is going with my motion. So one is negative and one is positive. And so that means that my F net x ends up just being my F applied. Okay. In this scenario, I don't actually know what my F applied is yet, but I do also know that my F net x is equal to ma. This is Newton's second law. We're told that we're accelerating, and so I can calculate my F net x using my mass times my acceleration instead. So my F net x is going to be the mass. And in this case, I'm going to have to use the mass of the entire train, like the locomotive plus the train car. So I'm going to add my masses together. And so I get a total mass of 1.14 times 10 to the 6 kilograms. And my acceleration was 0.12 meters per second squared to the west. So I'm going to multiply those by each other. And so I'm going to get an F net of 1.4 times 10 to the 5. And that's going to be in newtons. And we're traveling to the west. It's a positive answer. So that's part A. That's the net force happening on the entire train. Part B, we're looking for the magnitude of the tension between the locomotive and the train car. So we have to actually look at probably just the train car specifically. So we know the net force that's acting on the entire section. But we also actually know that acceleration is going to be the same for the locomotive and the train car. So in part A, we looked at the entire section together. In part B, we can actually look at specifically just the train car. And so if we look at the train car only, we have our F net X is actually just our tension. And so we can use the mass of the car times the acceleration that we know the train car is experiencing to equal our tension. And so the mass of the train car by itself was only 5 times 10 to the 5 kilograms. And the acceleration we knew was 0.12. And so then that's going to give us our tension. So we're just going to multiply those two. And so we're going to get a tension of 6.0 times 10 to the 4. And that's going to be in newtons. Okay, and technically we should say that our tension is 6.0 times 10 to the 4 newtons. And again, that is to the west in this case because we were looking at the train car only. Okay, so that's practice question number 1. All right, so we're going to move on to look at practice question number 2. So again, this is practice question number 2 coming from the force problems slide deck. So practice question number 2, we have 2 dynamics carts and they are placed end to end and we are pushing on one cart to cause the other cart to move. So let's just draw ourselves a little picture of what we've got going on here. So I've got cart 2. And it happens to be attached to cart 1. And they're not attached via a rope or a cable. They're just attached to each other. And then someone is pushing. And we're pushing with a force of 18.9 newtons. Okay, so let's just write down what we know from our question. So the mass of cart 1, so M1, is 1.2 kilograms. The mass of cart 2 is 1.8 kilograms. That's why I've drawn cart 2 to be a little bit larger. And cart 1 is being pushed with this applied force of 18.9 newtons. And it's traveling to the west. Okay, and so that's causing cart 1 to push on cart 2. And so we are first trying to look for the acceleration of each of the carts. All right, we always want to make sure that we draw our free body diagrams. So if we look at each of our carts, we can draw our free body diagrams, not on our system diagram, but let's draw them down below here. So if we look at cart 1, so it has an Fn because it's obviously on a surface of some kind. It's being pushed. And it has an FG. So it has FG1. And we know, so if we look back at our diagram here, we know that cart 1 is pushing on cart 2. And that means that cart 2 is also pushing back on cart 1. Okay, so since they're in contact with each other. So that means that cart 1 also has this force. This is the force of 1 on 2. And it's got that applied force. Okay. Cart 2, again, has our Fn. So this will be Fn2. And it's got an Fg, so this will be Fg2. And it's got that force that it's pushing back on cart 1. So this is the force of 2 on 1. But cart 2 doesn't have that applied force. Okay, so cart 2 is not directly being pushed. It's being pushed from the force that's coming from cart 1. Okay, and so that's where our free body diagrams look a little different, cart 1 to cart 2. Oh, nope, we got them backwards. I'm sorry about that. So I've actually got to flip these around. And so I just drawn them backwards here. There we go. This one is the force of 2 on 1. This one is the force of 1 on 2. There we go. That looks a little bit better. Okay. So cart number 1 has cart 2 pushing back on it. Sorry, I got those two confused. So cart 1 has cart 2 pushing back on it, and then cart 2 has cart 1 pushing forwards on it. And then let's just make sure that we label our motion in our problem as well. And so we're going to the left, we're going to the west in terms of our motion. Okay, so we are trying to find the acceleration on each cart, which means we can actually look at the entire system together, and we can find the acceleration for everything. So if we are looking at the net force on our x-axis, we are going to have our F applied going in our positive direction. And then we are going to have our force of 1 on 2 also going in the positive direction. But our force of 2 on 1 is going to be going in the negative direction. Now, those two forces are going to be equal to each other. And so they're going to actually cancel each other out. And so we are going to get our mass times our acceleration will actually just be equal to our F applied. Since in this problem as well, we're ignoring friction. So our mass is going to have to be the mass of both carts together. So we've got 1.8 kilograms and 1.2 kilograms. So we're 3 kilograms total. And we're looking for our acceleration. And our applied force was 18.9 newtons. So then our acceleration is 18.9 divided by 3. So we're looking at an acceleration of 6.3 meters per second squared. And we're traveling to the west there. All right. Part B, we're asking to find the force that cart 1 exerts on cart 2. So we're looking specifically only now at cart 2 so that we can look at the net force on the x-axis on cart 2, and it's only the force of 1 on 2. And so then we know that the mass of just cart 2, sorry, this should be cart 2, times the acceleration, which will be the same for each cart, will be the force of 1 on 2, which is what we're looking for here. So the mass of cart 2 was 1.8 kilograms. Our acceleration we calculated as 6.3, and that will be the force of cart 1 on cart 2. So we've got 11 newtons is the force of 1 on 2. And that's going to be traveling to the west again. We're going in that positive direction. Okay, now question C as part of this practice question, would your answers change if cart 2 were pushed with an equal but opposite force instead of cart 1? If your answers change, we'll calculate the new results. So if those two were changed, then we would actually end up with the same acceleration. And so our acceleration is not going to be any different. And so we're going to leave that at that for part C. All right, so next problem we're looking at is practice question number 4. So practice question number 4. In this practice question, we are going to have some friction happening. Okay, so in practice question number 4, we're going to be including friction. So we have a hockey puck, and it's moving west along the ice. So we've got our hockey puck here, and we know its mass. Oh, let's write this in red. So the mass of our puck is 0.170 kilograms. And it's initially moving, so we have a VI of 21.2 meters per second to the west, and it's moving along the ice. The coefficient for kinetic friction, so mu K, is 0.005. And we've got our motion for our puck going this way. We're traveling to the west. Oh, it does not want to create my arrow. There we go. So we have motion traveling to the left here. All right. So part A of this question says, what is the speed of the puck after traveling 58.5 meters? So we're traveling a distance now of 58.5 meters. And we're looking for what the speed will be after that 58.5 meters. Okay. All right. Now, here's our tricky part. So our hockey puck is going to be slowing down because it's encountering friction on the ice. So we need a free body diagram to have a look at our hockey puck. So our hockey puck has an FN that's acting up because it's resting on the surface of the ice. It has an FG that's pulling it down because it's got a mass, and so the force of gravity is pulling it down. And it has a friction force, so that's slowing it down. Okay, so the only force that's acting on this puck on the x-axis is our friction force. It's acting opposite our motion. And so what that means is that our F net x for our puck is negative Fk, right? We need to find the acceleration of the hockey puck. We have the displacement, we have the VI, but since we don't have the acceleration or the time, we can't find VF without one of those things. And so the easiest thing for us to find is going to be the acceleration, because we can use forces to find the acceleration of our puck. Now, we should be thinking about the fact that the acceleration should be negative because the puck should be slowing down when it's sliding across the ice. So our F net x is going to be our negative Fk. So we can substitute the mass of our puck times our acceleration. Hold on, we're going to try that one more time. So the mass of our puck times its acceleration is going to be our negative Fk. Now, we can substitute for Fk since we don't know what the force of friction is. We do know a formula for friction. And so Fk is really mu K Fn. Okay, and we're going to keep substituting in until we get to a point where we have the values that we know so that we can find that acceleration, because I currently don't know Fn. So we have our ma is equal to negative mu mk, and then Fn, since we're looking at it on the y-axis, it's actually equal to Fg. Now, as an aside here, Fn is not always equal to Fg, but it happens to be equal in this case because there's only two forces on the y-axis and there's no up or down motion, which means we're dealing with a net force of 0. We're actually using Newton's first law to determine that our Fn and our Fg will actually be equal to each other in this case. If there are more forces acting on the y-axis, Fn and Fg are not equal to each other. This is not an all the time equality. However, Fn and Fg are often equal to each other. Okay, so now we have our ma is equal to our negative mu k, and we know the formula for Fg is actually mg. Okay, so we can substitute that in. The nice thing about this is that it allows me to actually cancel out my mass, which means I don't actually care about the mass of my puck. And so then to solve this equation, now I have my acceleration is going to be my negative mu k times g. And so mu k I had was a value 0.005. G is always 9.8. So the acceleration of my puck is actually negative 0.049 meters per second squared, and that's traveling to the west. Okay, so now I can plug that into a kinematic equation to solve for my VF. So since I have VI and delta D and my acceleration, and I'm looking to find VF, I'm going to use this equation. VF squared is equal to VI squared plus 2a delta D. So my VF will actually be the square root of my VI squared plus my 2a delta D. So we're going to do square root. My VI was 21.2, and that's going to have to be squared. And then my acceleration was negative 0.049. And the distance that I traveled was 58.5 meters. So then I'm just going to do the math there. So 21.2 squared plus our 2 times negative 0.049 times 58.5. And then square rooting that, I get a VF of 21.1. Yeah, 3 sig figs. So that'll be VF is 21.1 meters per second squared. And again, that's going to be to the west. So the puck is definitely still moving. It hasn't slowed down by a lot. However, we know that its acceleration was relatively small. And so it wasn't slowing down by a huge amount. All right, so then part B of this question says, after being played on for a while, the ice becomes rougher and the coefficient of kinetic friction increases to 0.047. How far will the puck travel if its initial and final speeds are the same as before? So we want to go back in our formulas here, and I want to actually just go back to this section where we ended up calculating the acceleration. So the only thing that's changed for part B is that we have a different value for mu k. So this formula is going to stay exactly the same. So our acceleration is still just going to be our negative mu k times g. And so we're going to calculate our new acceleration in this new instance with a mu k of 0.047. And so our new acceleration is now 0.047 times 9.8 is now negative 0.46. Yeah. Okay, so now we're accelerating again to the west still, at a higher rate. So we're accelerating at a higher rate. But also in this part, our VI is our 21.2 meters per second. And our VF is going to be the VF from part 1, so it's 21.1 meters per second. And now we're looking to find our delta D. So we're just going to use a kinematic equation to solve for our delta D. So we have acceleration, we have VI, we have VF, and we're looking for delta D. So we're going to use probably the same equation. Our VF squared is VI squared plus 2a delta D. Only this time we're going to rearrange and look for delta D. So our VF squared minus our VI squared will be our 2a delta D. So then our VF squared minus our VI squared divided by 2a will give us our delta D. So our VF squared was 21.1 squared, VI was 21.2 squared, and then 2 times our acceleration, which is negative 0.46. So that's going to give us our delta D. So we're just going to do the math there. 21.1 squared minus our 21.2 squared divided by 2 times our acceleration. So we're getting 4.6 meters. Okay, so in this new instance, our puck is only going to travel about 5 meters rather than traveling 58.5 meters. Okay, so that's practice problem number 4. And so then the last one we're going to do is practice problem number 6. So we're looking at practice number 6 now. And so in practice problem number 6, we have 2 students pushing a piano. So I'm going to draw my piano here. Lovely piano. So I've got my piano, and the mass of my piano is 260 kilograms. It's a rather large piano. And Kathy and Matt are both pushing on the piano. Okay, so we have, and they're both pushing forward. So I'm going to choose that they're pushing to the right. So this is the force of Kathy, and then this one is going to be the force of Matt. And so Kathy's force is 280 newtons, and Matt's force is 340 newtons. And we are told that the piano is accelerating at 0.3 meters per second squared, and we're using the right as our motion. Okay, so in this case, we're looking for the coefficient of kinetic friction. So that means that we also have this Fn acting on our piano. We always have Fg, and then we must have this Fk that's acting on our piano as well in the opposite direction for our motion. So we are looking for the coefficient of kinetic friction. So we are going to have to look at that net force happening again on that x-axis. So our F net x, in this case, we're going to have the force of Kathy plus the force of Matt minus our Fk. And so our F net x is going to be our mass times our acceleration. And then we'll have the force of Kathy plus the force of Matt. And we know that Fk is really mu k Fn. And we can start doing some substituting here if you like. So the mass of the piano is 260 kilograms. The acceleration we knew was 0.3. The force of Kathy is 280 newtons. The force of Matt is 340. And then we also know that Fn is actually equal to Fg in this case. And so we're just going to do a little bit of math here as we're sort of collecting some like terms. So our 280 plus our 340 will be 620. And then again, we're subtracting our mu k, and we know that FG is really mg. So then our 78 is equal to our 620. Mu k is what we're looking for. Our mass here is, again, the mass of the piano, 260. And then our g is 9.8. So we got 260 times our 9.8. So that means that we have 78 is equal to 620 minus 25. So 2548 mu k. So then we're just going to rearrange this and solve for mu k. So we'll end up with our 78 minus our 620 is equal to our negative 2548 mu k. So 78 minus our 620 is negative 542. It's equal to our negative 2548 mu k. So then divide both sides by negative 2548. So our negative 542 divided by our negative 2548 gives us a mu k of 0.21. Okay. Don't forget, mu k has no units, so no units required there for mu k. And then part B of this question is asking us how long it will take for the piano to stop moving after pushing it for 6.2 seconds from rest. So we're looking at how long it's going to take the piano to stop moving if we start pushing it from rest and we stop pushing it 6.2 seconds later. This actually I don't want us to do. So we're going to skip part B of this practice problem, okay? I forgot to remind you to skip it in the original slide deck, but we're going to skip part B because it's actually a little too complicated. It's not a problem that we're going to need to have to do. So that's the end of taking up these practice problems. So again, there are 4 more practice problems, practice problems 3, 5, 7, and 8 that you should be doing on your own and consulting the answer key for. So that's the end of